Okay, here's your statement. Going to be some multiple of the square root of y when you have a uniform cylinder and a hole of fixed diameter for an ideal fluid, and water behaves very much like an ideal fluid, okay? So this is what governs the flow from that uniform cylinder. And this number here is just a multiple of the ratio of the hole diameter to the cylinder diameter. Well, cross-sectional area to cross-sectional area, sorry, not diameter. Okay? So if you know the numbers and one other thing, you can write down what this number is, right? Okay? And if that number comes out 0.03, then here's your model. Okay? Now, the rate. I've used dy dt for the rate, right? Okay? Well, guess what? There's another way of expressing this if you understand that the apostrophe here means this. It means you take y and you take its rate of change with respect to t, okay? So this is the rate of change now of y with respect to t in this case. You got to be careful about with respect to what, because that can get confusing, but you just keep that straight and you learn to keep that straight. Because if you don't, you get wrong answers and you fix them. Okay, now this is down the road. This is like in fourth semester calculus, but you can solve this equation in mid-October if you're taking a calculus course, if you start in September, okay? So like in less than halfway through the calculus course, you can solve this, okay? With some simple rules, some of which we're going to derive tomorrow, though you don't know it, okay? So you got y prime equals 0.03 square root of y. Well, you got to use the SQRT for the square root or the raised to the 1/2 power, right? We can put that into Wolfram alpha just as I've written it, except you've got to write that square root. You don't have a square root symbol, right? So you can adapt that. That's easy. And it'll tell you what the solution is. It's called a differential equation. Okay? You've got a formula that gives you the rate of change, the instantaneous rate of change, and you get the exact solution. Okay? Now there are going to be constants in that solution, but you know enough now to figure out what those constants are. So you can write out the solution. Okay? And that's pretty cool. Okay? So this is telling you what happens in any small increment, basically. And then you got this equation that just lies everywhere. Okay? This is pretty cool.